Now that we've looked at the physical consequences of conjugation, we can think about the chemical consequences of conjugation. And one of those consequences is that the rate of addition reactions of conjugated dienes is faster than the rate of addition of your typical alkene. And there are two main reasons for this. The first reason we can think about in terms of the molecular orbital view of alkenes versus conjugated dienes. And so we're going to just take the simplest approach that we can, and we're going to compare ethylene, right, the simplest alkene, to 1,3-butadiene, the simplest conjugated diene that we can have. And so the molecular orbital view of ethylene we have seen a number of times looks like this, right, where you have a bonding orbital and an antibonding orbital. So we're simply looking at the pi system with ethylene. So we have a pi bond and we have a pi star antibonding orbital. The pi orbital is when the two p orbitals are in phase with one another, and the pi star is when the two p orbitals are out of phase with one another. And of course, there are two electrons that reside in this molecular orbital view, and those two electrons reside in the pi orbital, right, creating that pi bond. Now, we also saw earlier in chapter 12 our molecular orbital view of 1,3-butadiene. So when you mix two ethylenes together, right, that you get, instead of one bonding orbital, you get two bonding orbitals, and instead of one antibonding orbital, you get two antibonding orbitals. And so here I've redrawn out the two bonding orbitals, right? The lowest bonding orbital is when all of the p orbitals are in phase with one another, and then the second lowest, well, the highest bonding orbital is when C1 and C2 p orbitals are in phase, C3 and C4 p orbitals are in phase, and there's a node between C2 and C3, right? And of course this, we say, is the traditional view of double bond, single bond, double bond. So we saw that when we mix the pi orbitals of ethylene, we get a pi plus pi, that's the conjugated. We get a pi minus pi, that's the traditional double, single, double bond scenario. Those are both bonding orbitals. And then, of course, we get two antibonding orbitals, pi star plus pi star and pi star minus pi star. And when we think about the number of electrons in the system, we know we have 4 electrons, and so we add those 4 electrons to the lowest orbitals, and we see that they all 4 of them go into bonding orbitals, 2 of them into the completely conjugated orbital, and 2 of them into the pi minus pi, or we sometimes refer to that as psi2. So psi1 and psi2 orbitals. Now, why is this important to think about? Well, when we're looking at reactivity, when we compare the reactivity of ethylene to that of 1,3-butadiene, we have to look at both the HOMO and the LUMO. And so with ethylene, the HOMO, where the electrons, highest occupied molecular orbital of the electrons, is in that pi system, and the LUMO is in the pi star. When we mix two ethylenes together, what happens is the HOMO of 1,3-butadiene is actually a little bit higher in energy than the HOMO of ethylene. Conversely, the LUMO of 1,3-butadiene is a little bit lower energy than the LUMO of ethylene by itself. The chemical consequence of this is that when you can increase the energy of the HOMO, it makes it more reactive toward electrophiles. And when we're looking at typical electrophilic addition reactions, this is the heart of the matter, right? It becomes more reactive because the HOMO is at a little higher energy. Now, also, if it's accepting electrons, which we're not really going to look at that much, but It also, when you can lower the LUMO, it actually becomes more reactive toward nucleophiles. So let's look at the second reasoning, and that is resonance stabilization of the transition state. So when a typical alkene reacts with an electrophile, so here I'm showing 1-butene reacting with an electrophile, I get, in this particular example, a secondary carbocation. So I get the formation of the most stable carbocation, right? So here is my secondary carbocation. Of course, it depends on what substituents are on that double bond, but in this particular case, I get a secondary carbocation. Now, when I compare that to the reaction of 1,3-butadiene with an electrophile, I see a little bit different scenario where I form an allylic carbocation, and that allylic carbocation has a resonance structure to it, right? So that resonance structure helps, we know, to stabilize that charge so that it's not building up on one single atom, but it is distributed in between both of the atoms, right? And so this is an allylic carbocation, which we know can be stabilized through resonance. And so let's think about the products of addition of HX, right? And then we'll look at the products of addition of halogens. And so the simplest example is reacting 1,3-butadiene with hydrochloric acid at minus 78 degrees. And when we do this, I'm going to number the carbons, and you're going to see why in just a little bit. So I'm numbering them 1, 2, 3, and 4. So when 1,3-butadiene reacts with HCl, notice in this particular example, I could react either one of the double bonds with HCl, and I get the same product, or products, as you're going to see. So I get this product, which we would think of as the typical addition product, right? And numbering the carbons 1, 2, 3, 4. I see how that is kind of laid out. Now, I also get another product, and I've labeled the carbons here as well. So we're going to see how both of these products are formed in just a little bit. And at minus 78 degrees, I see that the product distribution is 76% of the first addition and 24% of the second addition. And we're going to see that, depending on the conditions, we can actually vary the percentages of the products. The product on the left we call a 1,2 addition product because the hydrogen added to the 1 carbon and then the chlorine added to the 2 carbon. So this is what I would consider a typical addition reaction, 1,2 addition reaction. The product on the right is a little bit different, and so we see that the hydrogen adds to the 1 carbon, but the chlorine's actually adding to the 4 carbon, and the double bond is moving around. And that is what we call a 1,4 addition. So let's take a look at why that double bond moves around, and we can do that by thinking about the mechanism of this reaction. So when 1,3-butadiene reacts with HCl, the first step is your typical addition where the pi electrons are going to go toward that proton and then the HCl bond breaks. Right? So we can show it like this. Your typical addition reaction of HCl with an alkene. The result is an allylic carbocation, which we know we can stabilize, right? So we can stabilize that through resonance. And when I draw this allylic carbocation, I know it has a resonance structure. So these are the 2 resonance structures of this particular allylic carbocation. And the first one may weigh a little bit heavier than the second one, but in reality, there is a distribution of that positive charge throughout those 3 carbon bonds. And so a true representation of the allylic carbocation looks more like this, right? So here is my the structure of the allylic carbocation. And when chloride then attacks that carbocation, you see that it can attack either this carbon, which I'll label A, or it could attack this carbon, and I'll label that one B. So when it attacks A, you see that so the chloride is going to that particular carbon, and the double bond is going to in between the other carbons. But when I attack through the pathway B, right, chlorine is attaching to that carbon, and the double bond goes to the other carbon. And this is how I produce my two products. Now, we're going to see a very similar occurrence with the addition of a halogen as well. So again, I'm going to take 1,3-butadiene, react it with chlorine, minus 75 degrees, labeling them carbons 1, 2, 3, and 4, and I see I get a 1,2 addition, and I get a 1,4 addition, just like I did with the addition of HCl, or HBr, right? And I see that in this particular example, under these conditions, I get a 50-50 mixture between the two, and this simply is indicative of the chlorine. This has nothing to do with, that neither one of them is favored, because when I run this reaction with bromine, at minus 15 degrees, I have to run this at a little bit higher temperature because bromine isn't quite as reactive as chlorine is. Then, again, I get the same products, 1,2 addition of the bromine and 1,4 addition of the bromine. And yet this time the product distribution is a little bit different. And so it's very hard to predict what that product distribution is. And we're going to get into how we figure out which one of these products is going to be favored over the other under certain conditions.